This video is about radicals. This is the symbol. This is called a radical symbol. Some people know it as roots, square roots, cubed roots, stuff like that. So that's what I'm talking about here. So we know that if we raise 2 to the second power, that equals 4. In other words, 2 times 2 is 4. 3 to the second power is 9, because 3 times 3 is 9, and so forth. So 4 to the second is 16. Well, the opposite of this is called squaring, or raising it to a power. The opposite is taking its root. So in this case, the square root of 4, so we're working backwards, is 2, because 2 times 2 is 4. Square root of 9 is 3, because 3 times 3 is 9. Square root of 16 is 4, because 4 times 4 is 16. So they're working backwards. The opposite of squaring it is taking the square root, or the opposite of raising it to a power is taking the root of that power. So it's worth noting that there's sort of a 2 here, but we don't write it on the second powers. And it's also worth noting that the answer to this really is plus or minus 2, because negative 2 times negative 2 is also 4, and negative 3 times negative 3 is 9. So there are actually 2 square roots to 9. It's positive 3 and negative 3, and the same thing for 4. So we call this plus or minus. This is a symbol that we use to represent both answers. And the same thing can be said for third power. So we could say, I'll go down here, 2 to the third power is equal to 8, because 2 times 2 times 2 is 8. Or 2 times 2 is 4, and 4 times 2 is 8. 3 to the third power is 27, because 3 times 3 is 9, times 3 is 27. And 4 to the third power is 64, because 4 times 4 is 16, times 4 is 64. Well, you can take what's called the cubed root of 8. So you'd have a little 3 here. The cubed root of 27, this is going backwards, and the cubed root of 64. And so the answer to this is 2. The answer to this is 3, and the answer to this is 4. So we're doing the opposite. It's like multiplying and dividing. Here you're going 4 times 4 times 4 is 64, and you're saying what's the cubed root of 64? It's 4, because 4 times 4 times 4 is 64. It's not plus or minus, because a negative 4 times a negative 4 times a negative 4 would equal negative 64. So when this is an odd root, it's just a positive answer. When it's an even root, it's a plus or minus. Okay. So and you can do this for fourth powers and fifth and sixth and so on. It gets bigger really fast. So do I have an example of that? You could say 2 to the fourth power, which is 16. So 2 times 2 is 4, times 2 is 8, times 2 is 16. So if I took the fourth root of 16, you're saying what number times itself 4 times equals 16, and the answer is 2. Okay? In this case, it could be plus or minus 2, because that's an even root. Okay, and the same thing for 3 to the fourth power is 81. So the fourth root of 81 is plus or minus 3. Okay, so these are radicals or square roots or roots, and they're the opposite of raising it to a power. Okay. Some other things that are worth mentioning. You can't take the square root of a negative, for example, because there's no number times itself that will equal a negative. So we have a name for this. We call it imaginary, but we'll come back to that later on. I stands for imaginary. But you can take the cubed root of negative 8, for example, because negative 2 times negative 2 is 4, and 4 times negative 2 is negative 8. So negative 2 multiplied by itself 3 times is negative 8. So if it's a negative under the radical, and this is an odd number, then you should be able to take the root. Okay, this is all pretty self-explanatory, obvious, I think. Negative 27, the cubed root is negative 3, because negative 3 times negative 3 times negative 3 is negative 27. Okay, I want you to notice that if you take the square root of 16, you get exactly 4. That's called a perfect square. If you take the square root of 25, you get exactly 5, because 5 times 5 is 25. Any number between 16 and 25 is not a perfect square. So if you said, what's the square root of 17? You'd need a calculator to do it. There's a button with this radical on it. So you'd say 17 square root. It's going to be 4 point something. So 4 point something times 4 point something equals 17. It's going to be irrational. Just going to keep going. 4 point dot 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 dot. So there's no perfect square to this, and you can't break this down at all. Same thing for square root of 18, square root of 19, square root of 20, all the way up to 25. Anything in between here is not a perfect square. However, if you look at 18, you can break it down into the square root of 2 times 9 is 18. And there's a rule that says if you have a radical of a product like this, you can break it into separate radicals. So that's square root of 2 times the square root of 9. Well, the square root of 9 is a perfect square. It's exactly 3 times 3. So you can call this 3 instead of calling it square root of 9 and say that this equals 3 times the square root of 2. So you're breaking down this square root of 18 to look like this. You're not solving it. You're just saying that the square root of 18 is the same thing as the square root of 3 times or 3 times the square root of 2. On a calculator, if you plugged in 18 and hit the square root, you'd get the same answer as if you hit 2 and plugged in the square root and then multiplied it by 3. So you're not solving it, you're just kind of reducing it to a simpler form. Okay? So square root of 17, you can't do anything with it. It's not a perfect square. Square root of 16 is a perfect square. 18 can be broken down into a smaller numbers. Okay? And I think that's all I'm going to make this video about for now. There's a lot more to say about radicals. I'll make some other separate videos. Let me just do one more example for you. Square root of 28. It's somewhere between square root of 5 and square root of 25 and 36, because that's exactly 5 and that's exactly 6. It's somewhere in the middle. So I would need a calculator to figure it out, but I can break it down into, I'm looking for a perfect square. So I have 4 times 7 is 28, and I know that the square root of 4 is exactly 2. So I can call it this instead, and this is breaking it down. I guess one more thing that's worth mentioning, you should know the perfect squares by heart, I think. And so we have 1, which is 1 times 1, 4, which is 2 times 2, 9, 3 times 3, 16, 25, 36, 49 is 7 times 7, 64, 81, 100, 121, and 144. These are perfect squares, which means if I took the square root of this, I get 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So those are perfect squares. Definitely worth memorizing, easy to memorize. And then perfect cubes. 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 4 times 4 times 4 is 64. And 5 times 5 times 5 is 125. Beyond that, it gets a little harder to memorize, but these are some numbers you should be familiar with. These are called perfect cubes. Okay? Notice 1 is on both lists. You could also have perfect fourth powers. 1 times 1 times 1 times 1 is 1. 2 times 2 times 2 times 2 is 16. And 3 times 3 times 3 times 3 is 81. So these are fourth powers. These are third powers. These are second powers. Okay? So that's radicals, and you're expected to be able to take a radical and break it down into its smaller parts.